All right, so yesterday we talked about reducing agents, and we mentioned that we can make alcohols from ketones, aldehydes, esters, and carboxylic acids. However, we're really limited with the types of alcohols we can make. We can only make secondary alcohols and primary alcohols. Down here, we said that we can't make tertiary alcohols using sodium borohydride or lithium aluminum hydride for that matter, because the precursor would have relied on some sort of wacky Texas carbon, which doesn't exist. So we can't make tertiary alcohols via reduction. However, there's a workaround that we're going to see today, and that's using a Grignard reagent. So I'm going to start out with a little story about this guy. This is Victor Grignard. Victor Grignard is a French chemist that was practicing in the early 1900s, late 1800s, and he won a Nobel Prize in 1912. I was reading about him. He actually started out going to school in mathematics and failed out and decided to have a late in life career change into chemistry, and who knows, maybe we can all win Nobel Prizes if we fail at something a few times. All right. His Nobel Prize was for working with organometallic chemistry, which was brand new at the time. Really, organic chemistry was new at the time. Organometallic chemistry was really cutting edge. Quite obviously, he had the best mustache ever. So let's put that down. All right. The other historical trivia about him is he was a French chemist in 1912. If you're a history buff, what was going on around 1912? World War I. In World War I, all of the major chemists were kind of brought together by their local governments and said, you need to make us weapons that will help us win this war. So Victor Grignard was responsible for helping develop phosgene, one of the biggest chemical weapons used during World War I, in addition to mustard gas. So in addition to winning the Nobel Prize, he was also kind of a war criminal. It depends on who you ask. So helped develop chemical weapons. His counterpart on the German side was Fritz Haber. Fritz Haber helped deploy chlorine gas. So they were kind of alter egos. One was on the Allied side, one was on the German side. All right, down here, this is my best attempt to become Victor Grignard. This is me as a grad student. So I had a seminar that I had to present at in graduate school, so we all decided to grow massive mustaches and try to look like famous chemists. So I was aiming for Victor Grignard. I don't know if I really pulled it off. But we should put this down. Pretty good mustache. Yeah, I mean, I'm a humble guy. That was pretty good. All right, and I don't like chemical weapons. However, I like reading about them. If you get a chance, there's a movie out right now by Peter Jackson called They Will Not Grow Old. It was fascinating. He took 100-year-old footage and restored it, colorized it, and then took actual interviews with World War I vets. The weapons that they used during World War I don't think we really have a solid grasp today of how awful it was. Essentially, you would get a chemical burn on the inside of your lungs and on the mucous membranes in your eyes, and then you would asphyxiate on basically your own pus and fluids. It was pretty awful. After World War I, they basically decided as a community of chemists, no more. And so there were a lot of treaties proposed afterwards. And I think even Victor Grignard was part of the team that came together basically saying no more of this. This is getting out of hand. All right, anyways, it's a good intro for today. All right, let's talk about his chemistry. So the Grignard reaction was very cutting edge at the time. Prior to his chemistry and his research, there weren't that many ways of creating new carbon-carbon bonds. But what he found was if you take some sort of, let's say, alkyl halide, I think he was working with alkyl iodides, so I'll just do that one. If you take these alkyl halides and you mix them with magnesium metal, so what they did was they actually just put magnesium into a device that would turn it and create big ribbons of magnesium, mix these together for a while in an ether solvent. You have to use an ether solvent. You can't use anything else. You can actually insert the magnesium in between the carbon and the halogen. So it's a pretty cool reaction. The reason that this is really cool is if you think about it, the magnesium is really not very electronegative compared to the carbon. So the carbon is going to hog all of the electron density away from that magnesium. So another way of thinking about this is you can create something equivalent to a carbon having a negative charge, magnesium with a positive charge, and then your halogen hanging off the end. This carbon, once it has this super negative charge on it, is a really good nucleophile. However, it's also a good base. Which kind of brings us back to this point. When we're using the solvent, we have to use a solvent that's not acidic. Otherwise, we're going to do acid-base chemistry with our solvent. So let's make a note. And in addition to that, the ether solvent actually helps stabilize the magnesium during this process. It'll do Lewis acid-base chemistry with the magnesium metal and help stabilize the formation of your Grignard reagent. So it's a pretty simple process. You can do this with any sort of halogen. So this could be iodide, it could be bromide, it could be chloride. Those are typically the main three. You normally don't see it with fluorides though. So any one of those halogens will work for the Grignard reagent. All right, so let's take a look at this in action. All right, so let's say we've got acetone as our starting material. And I'm going to treat this with a Grignard reagent. This is methyl magnesium bromide in this case. All right. And actually, sorry, I'm going to change my colors here. Everyone's huffing now. All right. And if we think about acetone, acetone has a really strong dipole towards oxygen, right? So the carbon in that carbonyl is really electron deficient. And then we said that the carbon on this methyl group is really, really electron rich. So what we can do is we can have this carbon physically reach over, attack that carbonyl, and then kick up electron density onto the oxygen. And we've installed a new CH3 group into that position. All right. We also have the magnesium bromide floating around as a countercation at this point. However, usually organic chemists aren't interested in isolating the ionic species. They want a neutral compound. So in step 2, we need to introduce some sort of acid or weak acid. So I'm just going to show this as H+. That could be water, it could be an alcohol, it could be a variety of different things. And in this next step, we're going to grab that proton and we're going to make our alcohol. So you can see that this workaround allows us to make tertiary alcohols. And the coolest thing in my opinion is we've created a new carbon-carbon bond. We haven't really seen any ways of doing that so far. We've seen ways of cutting carbon-carbon bonds, but not creating carbon-carbon bonds. So this is pretty powerful chemistry. Does that make sense? I will say that this step right here is the second step. You can't mix your acid and your Grignard reagent together because, like I said, your Grignard reagent will want to do acid-base chemistry before it has a chance to do the nucleophilic attack. So you need to separate them into 2 separate steps. Yeah?
In terms of like rate limiting, how quick is the Grignard reaction?
So you're asking about relative rates of the reaction? It really depends a lot on sterics. And I will kind of put a disclaimer out here. This is the mechanism that the textbook shows. This mechanism isn't 100% correct. There's a lot of evidence that this mechanism is more radical-like than true nucleophilic attack. So I'm going to leave it the way the textbook has it just to avoid confusion. But if you are interested in seeing the more modern mechanism, I can show you that during my office hours. I like this one, though, because it's nice and clean and simple to understand, though. All right, let's do an example one. This time, I'm just going to give you the starting materials. You don't need to do the full mechanism, though. And then I want you to fill in the box. All right, step 1, I'll put above the arrow. This is phenyl magnesium bromide. And then step 2, I'm going to treat this with water. And I want us to predict what our new product will look like at the end of this reaction. If you want, you can do the mechanism down here. In fact, maybe that's a good idea. Yep.
Do we need to remember the first part of the Grignard reaction where the magnesium gets inserted between the carbon and halogen?
Yeah, so for example, let's say I give you a reaction where you don't have a Grignard reagent. You could say, well, I need to first have an alkyl halide. So maybe I need to do a radical addition of bromine and then add magnesium to make my Grignard reagent. So you should know how to make your Grignard reagents too. We'll do some practice, though. All right, so let's do the mechanism first. It's important to remember that the carbon attached to the magnesium is the nucleophile. It's the thing with really, really high electron density. And it's going to attack that carbon on our carbonyl. This could be an aldehyde or a ketone or an ester. It doesn't really matter. And then kick up electrons. And our oxygen will be kind of off to the side with a negative charge. Our phenyl group will now be covalently bonded to that carbon. And let me slide this over just so we can account for our magnesium as well. All right, and then step 2, we've got water floating around. And this oxygen can steal a proton from water. Oops, looks like I had hydronium there. And there we go. However, getting back to Leslie's point, we could make our Grignard reagent from bromobenzene by just simply adding in magnesium metal to that too, right? So if we wanted to, we could add that. Whoops. Holy cow, I saw hands pop up. I'm like, I made a mistake. I know I did. Here we go. I had it attached to the wrong carbon. I was thinking while writing, and sometimes that's not always good. All right, does that make sense? So the things we can add are pretty diverse. As you saw up here, in this top one, we added a methyl group. Down here, we were actually able to add a phenyl group. The hybridization of the carbon doesn't really matter too much for these reactions. It can be an sp3 carbon acting as your nucleophile, or it can be an sp2 carbon. So this is a really diverse way of adding nucleophiles into electrophiles like carbonyl group. I did want to warn you though, students get really tempted to do substitution chemistry with Grignard reagents, right? I've been telling you that these are really good nucleophiles. However, they're not very good at doing substitution reactions. I'll show you a reaction that is similar to a Grignard reaction later on in the year where you can do SN2 substitutions, but you can't really do SN2 substitutions cleanly with Grignard reagents. All right, let's do a little bit harder one. All right, we're going to do a few different ways of making one compound. Oops, that should be an alcohol. All right, so our target is this molecule. And I want us to have 3 different ways to make this one target molecule using different starting materials. So using what you know about Grignard reagents, propose 3 different ways through which you can make this one target compound. Okay, show of thumbs. Who thinks they got all 3 ways? Looks like most people got it. That's good. All right, so let's go backwards. Anytime I'm looking at these, we saw up above, we can basically install one of the carbons attached to that central group. So if we look at that one, let's just say we're going to install that thing circled in orange, right? That means that our starting material must have still had this isopropyl group and this methyl group coming off of it. So if we go ahead, we can say, all right, it must have been a ketone where one side was that isopropyl group, one side was that methyl group. They remain on our final product. And then we need to add in that ethyl group. Okay, so that means that our first reagent must have been what? Yeah, ethyl magnesium bromide makes sense. That would allow us to install that orange functional group that I've circled. And then step 2, we need to ensure that the alcohol is protonated. So let's just treat this with some sort of weak acid like water. So that looks pretty easy. All right. However, I arbitrarily picked that ethyl group. I could have said, well, maybe our starting material had the isopropyl group and the ethyl group on it, and we were trying to install this methyl group. That means alternatively, our starting material could have looked like this, and then we could have had methyl magnesium bromide, followed by water. Or we could have installed the isopropyl group, and maybe we had a methyl group on one side, an ethyl group on the other. All 3 of these methods would give you the exact same target. So this does allow you a fair amount of freedom when you are planning syntheses. Does that make sense? All right. Let's continue on. All of the reagents we've been working with so far have been ketones. Let's take a look at what happens with aldehydes, and then we'll jump into esters. All right, so in lab this week, some of you have already made this. What's this compound called? Benzaldehyde. It kind of smells like almonds. So let's say you've got benzaldehyde, and you treat it with methyl magnesium bromide, followed by your weak acid. We'll just call it water in this case. Let's try to predict what our product would look like. Once you get good at this, you don't even need to show the full mechanism unless you really want to. On an exam, I'll say show the mechanism if I want the mechanism. Either that or you'll have to learn to read my mind. All right, thumbs up if you got this one. All right, it looks like we're on track. If we were to add in methyl magnesium bromide, we would make this alcohol. The hydrogen on the aldehyde is still going to hang out right there, and then we would add in that new methyl group. If you wanted to, you can even label that as CH3 if you want. Alternatively, we know of another way of making this target molecule, and we saw this yesterday. Another route we could have taken would have been to start out with this molecule called acetophenone. And what reagent would we need to make that same target material? NaBH4, sodium borohydride, and some sort of alcohol solvent, maybe methanol. But the big takeaway is with alcohols, you don't make, with aldehydes, you don't make tertiary alcohols, you make secondary alcohols. And we saw yesterday that you can make secondary alcohols via reduction as well. So it's kind of expanding our toolbox. So if I give you a synthetic problem with a secondary alcohol, you could think I can make this with a Grignard and an aldehyde, or I could have made it from reduction of a ketone. You've got a lot more flexibility now. Yep. That's a really good question. So if we look at this, we've created a new stereo center. We're not going to be able to control whether or not we're getting the R enantiomer or the S enantiomer. You're going to get a racemic mixture of 50-50. So let's even make a note of this. It's going to be a racemic mixture. Good point. All right. So now let's jump into a different functional group. Let's go into esters. We've done ketones. We've done aldehydes. Now let's do esters. So we'll do a similar ester to the one we were just working on, but this time let's try to do the full mechanism together. This is called methyl benzoate, and we're going to treat this with ethyl magnesium bromide in excess. That's going to be step 1. And then step 2, as always, is going to be our quench with water. All right, so just like with any other Grignard reaction, we know that the ethyl group is going to be our nucleophile. It's going to attack into the carbonyl, kick up electrons onto that oxygen. And we were able to install this brand new ethyl group onto that central carbon. The problem at this point is this is really unstable. We saw yesterday an example of this where it was unstable as well. What do you think could happen at this point? Resonance? That's a solid guess. It's important to remember that these oxygen groups can act as kind of leaving groups. So in your next step, the electrons hanging out on this oxygen will actually dump down and eject off the leaving group, which was formerly the oxygen on your ester. So now that ethyl group that we installed is hanging out right here. The oxygen that was kicked off is hanging out over here. I'll just write CH3 on there as well. All right, we still have more excess ethyl magnesium bromide that's still floating around. So in this next step, now that we've created a ketone, that ethyl group can attack in to our newly formed ketone. We really can't stop at this unstable intermediate. It will want to form the ketone whether or not you want it to. All right, so now we're going to install our second ethyl group. This oxygen's got a negative charge. And then last but not least, we're going to treat this with water. This oxygen, steal the proton from water. And unlike with aldehydes, we're going to make a tertiary alcohol. What students often forget with this is you'll always go through a ketone intermediate. And then you have to attack that ketone intermediate with excess reagent. Yep.
Is that methoxide also going to deprotonate the water and become ethanol, or do we just not care about it?
Yeah, that's a good point. So if you want to get fancy, you could account for this stealing a proton as well. Oftentimes it's just kind of neglected because it's a byproduct, and we're really not that interested in saving our byproduct. Yep.
So exactly the magnesium bromide compound that you make as a byproduct, what's the actual process of removing that once you're done with it?
Oftentimes you can do it with simple acid-base extraction, so you can purify it that way for simple systems. If it's really messy, oftentimes what you need to do is chromatography to help clean it up. And chromatography can be a very involved process. Other times you can get away with distillation, things like that. It really just depends on the physical properties of your product and how clean your reaction ran. Yep. So the main thing to remember is anytime you see an ester in a Grignard reagent, it's a lot more involved than you would think at first thought. Does that make sense? All right, let's do the last one. So we've done our ester, we've done our ketone, we've done our aldehyde. Let's do the carboxylic acid. I'm going to zoom in a bit. So we'll do benzoic acid, and we'll do ethyl magnesium bromide. In fact, let me show my bonds more clearly. All right, so what do you think will happen with a carboxylic acid? Check with your neighbor. All right, does anybody have an idea of what would happen and want to share it? Nobody? Acid-base chemistry. Fastest reaction in chemistry is acid-base chemistry. Before anything else can occur, it will steal the proton, and you'll form your carboxylate salt. At which point, I'd be asking my student that was trying this, why the heck are you deprotonating your carboxylic acid with a Grignard reagent? There are a lot easier reagents that can be used. So the big problem with Grignard reagents is it will not work if you have any sort of acidic protons in your starting material. So that's a big, big caveat to these reactions. So this is a pretty big issue for chemists. It limits our starting materials to really simple starting materials that don't have any acidic functional groups like alcohols or carboxylic acids. Alcohols are even acidic enough to be deprotonated by a Grignard reagent. So we have to get really, really creative. And in order to prevent this unwanted acid-base chemistry from occurring, we actually have to protect our acidic functional groups. So let's talk about functional group protection. All right, So let's take an example one. Let's say we're treating this ketone with methyl magnesium bromide. What would our product look like? Would it add into the carbonyl? No. Fastest reaction would be deprotonation. Where's the most acidic proton? On the oxygen of the alcohol, right? So we would make an alkoxide at this point. That oxygen would have a negative charge, and the reason being that this is too acidic. It must be protected. So then you've got to go into your chemical cabinet and you've got to find a protecting group. There's a bunch of different protecting groups you can use. We're just going to learn one in this class. In fact, you can buy a whole volume of books about protecting groups. It's a pretty widespread field right now. So let's talk about different protecting groups. All right. So anytime you have an alcohol and you want to use a Grignard reagent, you need to protect it. The most common protecting group are silanes. And usually the one you'll see in our textbook is trimethylsilane. Let me put this down a little lower. Whoops. And the other name for this is TMSCl. The TMS stands for trimethylsilane. And the TMS is really doing the protecting portion of this. The chlorine is just acting as a leaving group. All right, so in this first step, your alcohol is going to attack the silicon and kick off the chlorine. I know last term I told you you can't do SN2 substitution on tertiary carbons. Why do you think it's allowed in this case? It's not carbon. If you look at the periodic table, silicon is right below carbon. It's a lot bigger, so it'll actually fan out those methyl groups a bit more so that the nucleophile can actually attack in onto a tertiary silane. So SN2 is allowed here. And typically, in the next step, you have some sort of non-nucleophile base that will deprotonate your alcohol. Oftentimes, this is triethylamine or some sort of amine base like pyridine. You can steal this proton. Oops, let me be consistent. And like I said before, this whole group can be abbreviated as TMS. So if you wanted to, you could kind of trim this down and you could just write R-O TMS, and that would indicate that we've got a TMS protecting group coming off of that oxygen. Make sure when you write this out, though, that you keep TMS in order. You don't want to write SMT. People won't understand what that means. Yep.
Never mind. I thought that the I was alone here and the silicon.
Oh, no, that's just part of the silicon. Yep. All right. At this point, though, there are no protons that are acidic on our starting alcohol. We've blocked it with this TMS placeholder. Okay, so now let's see how we could use this to solve our problem that I just showed you up above. we need to protect that alcohol coming off the very end. So in order to do that, we could just really quickly say, all right, we need TMSCl as our first reagent. We need some sort of base to facilitate that final deprotonation. Whoops, that should be a 3, not a 2. And then we can protect that alcohol coming off the very end and block it from doing any sort of acid-base chemistry. Now, if we want to, we can treat it with our Grignard reagent. And up above, let's go check. We use methyl magnesium bromide. And then step 2, we'll use water. Let me fix this reaction arrow. Let's predict what this product would look like. Give me a thumbs up if you think you got this one. All right, that's good. I think we're making good progress. All right, so after our Grignard reaction, we'll have a new methyl group installed in. So we'll have an alcohol coming off the right-hand side and then a protected alcohol on the left-hand side. All right, now the big thing we've got to do is we've got to get rid of this TMS group and convert it back to the original alcohol. And the way we do this is a couple different ways. The first way is either treat it with acid, or the more common way is to use something called TBAF, because we can never have enough acronyms in our lives. Oops. And when you do that, that'll remove that TMS protecting group and convert this back to your original alcohol. All right, just for fun, let's name this alcohol. Yep. Yeah, so NET3, sorry, going backwards. Looks like that. It's just a non-nucleophilic base. And we saw that we needed a base up in this step to remove that proton to get us to a neutral species. So really it's just acting as a weak base, but we don't want it to do any other chemistry besides acid-base chemistry. Yeah, good question though. All right, so what would this diol be named? Everyone's like mumbling at me, like, okay.
Should be 4-methyl, 1,4-pentane diol.
Oh, yeah.
What's that?
The other way around.
4-methyl, 1,4-pentane diol.
So that's a good question. Which way should we number? We want our alcohols to be at the lowest priority. So it'd be 1, 2, 3, 4, 5. Got a methyl group coming off here. So this would be 4-methyl. 1, 2, pentane.
1,4.
Oops, sorry, 1,4-pentane diol. So you can go through and name some of these diols. But remember, when you are numbering, you want to number so that your most important functional group has the minimized numbering. So in this case, you want to minimize numbering for the alcohol. All right, so let's take a look at what the heck TBAF is. This is tetra N-butyl ammonium fluoride. It just rolls right off the tongue.
Oh, yeah, does it?
So TBAF, that's the thing that will remove the TMS protecting group. We're not going to get into the mechanism behind that, but it's a pretty interesting compound. So we've got all these butyl groups, and we call them N-butyl groups because they are not branched. They're a straight chain, so they're normal butyl. We've got 4 of them, so that's the tetra portion of that. And then we've got fluoride floating around as an anion. Really, when it comes down to brass tacks, the fluoride is the thing doing the deprotection. Fluoride really, really, really wants to form a bond with that silicon. It'll find any way to do that and then basically kick off that oxygen as a leaving group. So there's a bunch of different fluoride-based deprotecting groups. And there's a bunch of other protecting groups beyond just TMS. So for example, you can have TIPS, that's triisopropyl silo. You can have a bunch of other ones. Usually when you look in the literature, TBAF is the weapon of choice to get rid of your TMS protecting group. Yep.
Why is TBAF used over like theft? Something instead of like you wrote up top like
So you're asking why don't we just use acid? Yeah, that's a good point. So acid really only works for TMS. It won't work for any other protecting group. So for example, TIPS, triisopropyl silo, acid won't touch.
But TBAF would work for any of them?
TBAF is universal. It'll kick off almost any silyl protecting group. So that's why it tends to be the go-to.
Is it cheaper and like easy to get, or is it kind of?
That's a good question. So it's not cheaper or easier to get. I will say that the textbook we use loves TMS. Most chemists don't because it will fall off even in the presence of a very, very weak acid. So chemists in practice tend to use stronger protecting groups than TMS, like TIPS. And in that case, you would have to use TBAF to remove it. Yep, good questions though. All right, that's where we're going to stop today. Tomorrow we'll come in and talk about reactions of alcohols.